Now that we've done some examples, we're going to prove the art gallery theorem. The art gallery theorem states that any museum with n walls can be guarded by at most n over 3 guards. So here's an example of a generic room that somebody might design for a museum. And when we put a guard in the room, the guard can only see 360 degrees around. So there are parts over here, for example, that this guard could not see. So we want to say how many guards do we need to plunk into this room? And even better if we can say where to put them so that every wall is visible to at least one guard. Okay. Now, without knowing what polygon we have, we came up with a case where we needed n over 3 guards. So we want to say that that was actually the worst case, that it can't be worse. To prove this, we need to turn it into a more mathematical statement. So that's the first thing we're going to do. So what we're going to do is we're going to put a vertex at every corner. A corner is where two walls meet. So put a vertex at every corner. And then that's going to give us n vertices of an n-sided, those sides are the walls, polygon. Again, it's not necessarily convex. So here I've drawn a 12-sided polygon, 12 walls, and 12 vertices as well. Okay, so for this example, we should only need 4 guards. But again, where could we put them? We'll keep working on this. The idea is to look at the answer, if you're already given it, and let that guide you. When I'm thinking of polygons and I see the number 3, I immediately think of triangles. So that's what we're going to do. We're going to try to turn this into a bunch of triangles. And the way we do that is we're going to draw non-crossing triangles on the interior of the shape. So we're going to draw non-crossing triangles inside, well, let's call them diagonals, non-crossing diagonals inside the polygon P until it is all triangles. This is called a triangulation. Let's see it in action. So what I'm going to do is I'm just going to pick some places here. I'm going to put a diagonal here. Okay, well, this isn't all triangles, so I'm going to keep going. Now, I cannot do something like, it would be really, really bad if I do this. This is not okay. It went outside my shape, so that's not allowed. So I only want to connect vertices that is going to leave me with lines inside my shape. So I can draw this one here. Now again, I'm not quite a triangle. Now here you can see I have 2 choices. I can make that line or I can make that one. And it doesn't much matter which one I do. So I'm just going to do this one. Oh, that was the wrong pen. I'll do this one, and then maybe this, 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 this. So I'm just going through and I'm throwing in diagonals until all I have left are triangles. So now we can see that this is a triangle, triangle. All of these interior faces are triangles. So I have succeeded. The question is, can I always succeed? And yes, I can. That's something that we need to prove. It's a lemma. It's a fact that comes up in the middle of a proof that you realize, it would be really helpful if I'd already proved this. This is a statement that's not specific to this proof, but it's certainly useful for it. And so that's what we'll call a lemma. And the lemma is every polygon can be triangulated. There's never gets to a point where I can't keep going. Now, how would we prove this? Well, the easiest way to prove most statements about polygons is by induction. Polygons have n edges for some value of n. So that's what usually we want to do induction on. So that's what we'll do in this case. So I want to prove this lemma, and then I'll continue on with my proof of the art gallery theorem. But first, let's prove this lemma. Small proof for a small lemma. We're going to do induction on n equals the number of vertices, which is also the number of edges. So we need a base case. Let's take our base case to be the smallest non-trivial case, which is n equals 3. Then P is equal to a triangle, so we're done. A triangle can be triangulated because it already is. So now we get our inductive hypothesis. Our inductive hypothesis, any polygon with strictly fewer than n edges can be triangulated. That's our inductive hypothesis. And now we're going to assume that we have a polygon P with n edges. And we need to somehow reduce it. Now we know that n is at least 4 because we've already done our base case, and that's going to be helpful. So what we were going to do is we're going to think about how can we really work this. So we're going to use the generalized pigeonhole principle. So because a polygon is a closed shape, we know that at least one of the vertices has a convex angle. So let's say that by the pigeonhole principle, there exists a vertex A that is convex. So what do I mean by convex? I mean it's less than 180. So here is my vertex A. This vertex exists, okay, by the pigeonhole principle. If there's no convex angle, then when you add them all up, you're not going to end up closing back up. So there's a convex angle. So think about A, and let's say that A connects to 2 other vertices, which obviously does. So A can connect to B up here and to C down here. Okay, so I'm just defining B and C to be the guys connected to A. A is connected to 2 vertices because it's a polygon. Okay, I'm going to have 2 cases that I'm going to split this into to solve my problem. So I can see there's a nice easy case. So I'm going to copy this guy and I'll bring it over here and we'll do case 1. What if BC is inside P? Then I can just connect B and C with a diagonal. And let's think about what I've done there. Now I've sort of split my shape off. So now I've got the rest of my shape going here. And so I'm going to call this P prime. And think about how many vertices does P prime have? Well, I've taken off A and I've added this wall in here, right? So I've added this wall and I've taken off A. So P prime, this can be triangulated by the inductive hypothesis. So now I have a full triangulation of P because I triangulate P prime and then I've got this triangle here. So in this case, I'm done. That's case 1. But it's not necessarily true that BC is inside P, right? For example, if, let's see if I can find a good one. Okay, well, this isn't the best example I could have drawn. Oh, here's one. So if this is A, this would be B, and this would be C, and I can see that by connecting them, I go outside. I go outside my shape, okay? So that's the other case that I've got to deal with. So case 2 is when BC is not inside P. It's not fully inside P. Okay, for that case, let's bring this guy over here. What am I going to do? Well, I know that eventually I'm going to hit something that is inside. So here's some interior angle, Z. And what I want to define Z to be is as I drag this line connecting B and C back through my shape, I want Z to be the last thing that I hit. So if I take this example again here where I had A and I look here, this would be Z. It's the last thing I hit before I'm fully inside the shape as I sort of slide down in this direction with my line BC. Z is the last thing that I hit, okay? And now, well, how does Z help me? Well, because I know that this line is going to be inside my shape. And I know that this line is inside my shape and this line is inside my shape. So now what I can do is, again, I'm going to apply the inductive hypothesis. I'm going to cut A off. And now I still have this vertex Z, but now I have one fewer vertex. So I'm doing induction apparently on the number of vertices, not the number of edges, but they're the same. So here I'm going to let P prime is going to be without A, but now I've added in these extra lines BZ and BCZ, okay? But I've deleted A entirely from my shape. So P prime, again, this can be triangulated by the inductive hypothesis. And so that means that now we're done. And those are the only 2 cases. So this proves the lemma. So we can indeed always do this to our museum. We can always break our museum into triangles. How's that going to solve the problem? Well, you know that each triangle is convex, right? You can't draw a non-convex triangle. So I could put a guard inside each triangle, but that's not going to solve the problem. Here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have n minus 2 triangles. So this tells me that n minus 2 guards suffices, but we want n divided by 3. So we're not quite done. We'll have to think, how can we use this in order to get to this n over 3 guards? And we'll do that next time.